Okay, so the next I'm gonna shift it to this quasicrystalline spin network that we build from E8, and hopefully it can be the possibility space that we can use to model physics. And then Ray and Marcel are already using it. So how do we build it? How did it, how did we discover it? So I'm just giving you two methods. One is using the Fibonacci multigrid, and the other one is from E8. So the Fibonacci multigrid also is from two different methods. So first, I don't know, you guys, since you guys are not so familiar with quasicrystal, right? And then you're probably not familiar with the pentagrid, which is a dual grid to generate the penrose-Allen. Just like I'm quickly go through this. So 5, vectors that has the 5-fold symmetry. And so from each vector, we generate a set of plane that is perpendicular to that vector. And so 5 sets of planes equally spaced. So this gives us a grid space, right? And then you can see these arbitrary closeness, and then just like things are random, and you don't have a finite set of basically prototiles. So this is not a quasicrystal. It's not defined as quasicrystal. But if you take a dual of this grid space, meaning like at each intersection, you build a tile there. These are perpendicular, this is perpendicular. So at each intersection, you build a tile, and you shovel, you kind of move the tile a little bit. And so so that's why, these 5 tiles will become like something like this tile, the space. So eventually, if you do to all the intersections in this pentagrid, and you got the penrose-Allen. So that's a quasicrystal because it has only finite set of prototiles, finite set of the vertex types, and it does not have arbitrary closeness, all these kind of distances to 1 there. And so this is, from something that is not a quasicrystal to take a dual and generate something that is a crystal, quasicrystal. Okay, so, but is there another way to generate a quasicrystal? So what we did is instead of equally spacing these lines, we space them with the Fibonacci sequence or Fibonacci chain. So it has like a, see that this is a long distance, it's a short distance, it's a long, long, short, long, long, short, long, short. Okay, so the ratio between the long and the short is the golden ratio. So here, if you look at this structure, now there's no longer arbitrary closeness, and then there's only finite types of prototiles. And I cannot just like literally show you here, but
how do you find arbitrary closeness? Probably it might be
arbitrary closeness mean like there can be 2 intersection point, can be any distance between them. Yeah.
But there's an infinite set of distances between
two
objects.
2 points. Yeah.
In the infinite version, there's an infinite set. So it defines it as not a code because it has an infinite set of characters.
Anyway, so this is a quasicrystal now, but just instead of equally spacing these grid, if I just like space them with a quasicrystal spacing, because Fibonacci chain is a quasicrystal. So if I use the Fibonacci chain to space this grid, they become a quasicrystal. Okay, so just just so you have an idea of from a grid, equally spaced grid which is not quasicrystal, and into a Fibonacci spaced grid which is a quasicrystal, and that's how we generated the QS later.
So this is the De Bruijn method.
This is what?
This is what is the De Bruijn method, right?
De Bruijn method is take a dual to generate the quasicrystal.
Oh,
yeah, so this is like a, this is a different quasicrystal.
This is kind of our method.
Yeah, it's our method.
It's
okay.
More direct. It's a better direct way,
Yeah. So here. We didn't do the amount tiling for this one.
Same way. It's the same thing. You can generate.
So for amount tile, you use dodecahedron. Dodecahedron has 12 faces, right? So then you have 12 faces. 2 of them are parallel. So then you have 6 set of parallel planes, and then the planes would intersect a point. At each point, if you build a 3-dimensional tile, which is a rhombohedron, that's how you generate amount tiling. Yeah.
Fine.
Yeah.
We need to have a 5 line intersecting in the middle for this to work or not?
5 line intersect at the middle.
Yes.
I don't think that has to be true.
You can have some translation after that and it still work?
I believe so, but that's a good question. Yeah, I believe so.
Because I believe that the fact that now it's a quasicrystal depends on this condition. Otherwise, you can again go to the
Yeah.
same conditions and with the non-Fibonacci space.
Yeah, it could be like if it's if this is not intersecting, if it's in between, if it's any distance, if it's not the golden ratio division of this distance, then yeah, you're probably right. We probably have to. Anyway, so this is a 3D equivalent. This is the icosahedron. There are 6 directions or 12 directions. No, 10 directions, sorry, to 20 faces, so 2 parallel faces, 10 directions. So we set out like a 10 parallel plane sets. And so then these 10 parallel plane sets would intersect with each other and form different kind of cells. And so if I just plot out this tetrahedron cell, this is what it looks like. I mean, it's messy. It's a 2-dimensional view of a 3-dimensional grid space. So all you can kind of, you want to know from this structure is it's not a quasicrystal because it has different kind of cells, like infinite number of them. Okay, so then what if instead of equally spaced in the plane, we do a Fibonacci spacing? That will become quasicrystal. But before I go on to that one, so this is something that is, first of all, just remember this is not a quasicrystal yet, but it's made of 10 plane sets equally spaced. And then so if you would plot out the tetrahedron cells in this grid space, you can notice that you could plot the cells kind of like this or like this. If you look at the structure at the core, one's left twisted, the other one's right twisted. And so this is like, you could have both twisted together like this. They share the same point space.
So Fang, it's very easy to miss how remarkable this is. If you could please go back one slide, I just want to say a couple sentences. This just totally blew my mind when we discovered this. Fang is saying that she simply takes the 6 parallel plane classes. So the 10 parallel plane classes. So on each side you have an opposite. So then she's got this thing that is this periodic set of planes here, periodic set of planes here, and then she simply Fibonacci spaces them, right? And then what emerges all by itself is this constellation of regular tetrahedra.
No,
so
I don't have to Fibonacci space them.
Oh.
I already have that.
Yeah, thank you. Yeah. So
after Fibonacci space them, that's when they become a quasicrystal.
Yeah. So why would regular tetrahedra just come by this even spacing of a bunch of planes? It was not intuitive to me when this first resulted, and then for us to later find out that the Fibonacci space version holds in it all of the legal states of the E8 to 4D sliced and then compounded one. We didn't predict that either.
So anyway, so this is a grid space. It has left and right kind of twisted tetrahedron. It's not a quasicrystal because of the arbitrary closeness. So remember, we got some structure like that. And that structure is equivalent to 5 sets of a tetragrid. So if you just have a tetrahedron, which has 4 facets, and if you just equally space these 4 faces, and so you get a grid space kind of like this. And it is, in this case, it's a FCC, it's a crystal grid. But if you take the grid space, like the center of the grid space, for example, has 4 tetrahedron, gold tetrahedron, 4 cyan ones, and the opposite to each other, the orientation. And then let's forget about the cyan one for now, and take these 4 yellow ones, and then make another copy of the yellow one. Let's mark that it red, and so to compose them so that this angle, this relationship between this tetrahedron and this tetrahedron is the same as the relationship between this tetrahedron and this tetrahedron. You can see. And then you make a green copy, which will be like this tetrahedron, and then blue, and then purple. So then you build the 20 group, like this 20 group is there, right? So just by attaching different of these 4 groups together, so we got a 20 group. And so remember, each of the gold 4 is a whole tetragrid like this, and it has both the pointing down tetrahedron and the pointing up. So if you only look at the pointing down, it's a 20 group like this. If you look at these pointing up ones, oops, and they are actually this 20 group. So this is made of all the pointing down tetrahedron. This is the pointing up tetrahedron. And you look at this is like twisted that way, and that one is twisted the other way. If you superpose them together, they share the same point set. Okay, so then that's why I was telling you guys, like in a grid that we talk about, the Akasa grid, there is a left and a right, and then if you superpose them together, there is a left and right kind of superimposed. They share the same point set. And so here, just to show you an example from the even distributed 20 group to this that I talked earlier. And so, okay, so far it's always equally spaced. No matter it's the tetragrid or the Akasa grid, they're equally spaced. So then what I did is I just simply like changing the equal spacing to Fibonacci spacing. See, that's a short, long distance, short and long, just doing like that, something like that. And then this messy structure becomes actually something like is like interesting, because these kind of 20 groups start to show up everywhere. These look like exactly like the center 20 group. So as in the previous structure, there is only at the center that is a 20 group, and so there's a center that is a 20 group, and then because each one corresponded to a tetragrid, right? Going infinite. So if you look at the whole structure, extended structure, there is no 20 group anywhere. And so, but after I Fibonacci spaced it, there are 20 groups showing up everywhere. And then this is like to look at the whole structure and then look at the vertex types, just to take a point and see what's its neighbor looking like. This is just to give you some idea of what the neighbors could be looking like in that structure. And so the other method of generating the QSN is by, now that we know the alpha-salon quasicrystal, right? It's a cut and project from E8. So this is a 4-dimensional quasicrystal. We can take a 3-dimensional slice of the 4-dimensional quasicrystal, and we will get a 3-dimensional quasicrystal. The 3-dimensional quasicrystal can have a icosahedron symmetry, which is I'm not going to talk about here, or it can have tetrahedron symmetry like this one. This is a 2D projection of a 3D thing. If I rotate it, you can see, there's a 4 tetrahedron at the center, and then these are all just tetrahedron, and they're Fibonacci spaced. They're already automatically Fibonacci spaced if we take a 3-dimensional slice of the 4-dimensional quasicrystal, alpha-salon quasicrystal. So if I would put 5 copies of these together, the same way like how I did it to this tetragrid, right? I can put 5 copies together in the same way, and this is what I got. And so there's another way of slicing the 4-dimensional quasicrystal. The 4-dimensional quasicrystal at the center, it's a 600 cell. If you make a slice through the center, you can catch 4 tetrahedrons, right? And that's what it happens. At the center, you see 4 tetrahedrons. You can also slice the 600 cell on the faces, because 600 cell has 600 tetrahedron facets, right? If you slice through a facet, then the center would be 1 tetrahedron. Here, the center is 1 tetrahedron. So then, if I only have 1 tetrahedron there, how do I compose the 20 group and make another 19 copies and I put them together. That's a 20 group there. And these are the other tetrahedron, you know, these ones that it carries. And you can see these little 20 groups shows up everywhere. And then if I don't put the tetrahedron together to form a 20 group, if I put this center tetrahedron together to form an evenly distributed 20 group, then my structure would look like something like this. But if I rotate the tetrahedron from evenly distributed, you know, arrangement to the 20 group twist there, and then all these other tetrahedron also come together to form the same shape. So that kind of shows this kind of composition is doing some magic there. Okay, so then we get some structure, and we get this red structure, we get this cyan structure, right? We get two structures from E8 right now. E8 to acetylene quasicrystal, and we compose the slices together, we get this. But this is not the QSN. You know, the QSN means the Fibonacci space, you know, Akasa grade. So this is not QSN, because if I superimpose them together, the yellow tetrahedron is from the QSN, and the cyan or the red is from the E8. So basically the red is a subset of the cyan, and the cyan is a subset of the QSN. So then how do we get QSN from E8? We only get a subset of it. So what I tried to do is in E8, instead of selecting this kind of layer, the regular kind of layer, like using the Bruijn cell, you know, to get acceptance window to project down, I actually select the window that's bigger than the acceptance window. So then I get more tetrahedron from E8. When I project it to 40, I also get more tetrahedron. And then so as I enlarge that window slowly, I can see these cyans slowly become the red, get richer and richer until it actually equals this. But I don't have a proof to this. I only have a visual proof. I haven't had time to just mathematically prove it. So this is, you know, shows you another method from E8. We can thicken the window, and then we project to 40. We make slices, and we compose them together to get a QSN.
And I'd like to relate this to the possibility space notion of inflation and deflation that I talked about. So as she thickens the cut window in the higher dimension, what she does is she inflates the quasicrystal in the projective space. So what we want to do with our binary or trinary actions is make legal state selections that are deflations of the denser possibility space.
Yeah, so this is a review of that. You know, we can build an Akasa grid, which is a grid of 10 plane sets equally spaced. And then I use the Fibonacci space to space this grid, and I got Fibonacci Akasa grid, which is the QSN. We named it QSN later, but I didn't change in this slice. Or we can take a tetragrid, which is like parallel 4th plane set, and we Fibonacci space that tetragrid. We become a Fibonacci tetragrid, and then we golden composition, meaning like you know, like from 5 sets compose them together. Okay, in this way, you know, you take a 4, another 4, another 4, another 4, so it makes 20. So that also get the QSN. Or from E8 to acetylene quasicrystal and make a 3-dimensional slice. And then we compose this slice together to get that. So 3 different ways of achieving the same thing. So then whatever coding that we can do in E8 or the acetylene quasicrystal, we can think about this one-to-one relationships. Like what I said, like this kind of 30 tetrahedron rings or the Hope fibration. I wanted to kind of translate it to the QSN, but that part, I haven't had time to work on that yet. And I don't know what Marcelo's, you know, the progress on his part. So
Sorry, what's written in the center of the slide?
I don't know.
It's her Greek sorority letters
Something
from UCLA.
Something, something
Why
showed.
don't you know?
Something showed up. I don't know.
It's just
I
code
didn't-
that showed up.
A secret message from Pythagoras.
Yeah, so I don't know. Yeah. Okay, so yeah, just this is the last slide of this talk. So I'm just saying the binary selection, from it can be directly mapped to the selection in QSN, it's a possible space. And then Ray has given some, proposals on the coding in QSN. And then Marcelo also has done some, but Marcelo's approach is also from E8. So that's it for this one. And then if you guys can, don't need a break, and then I can just finish the next one. Next one is kind of short.
So we're wondering if Fibonacci anyons can be helpful in understanding our code that we don't know what it is. See, we don't know the code in the QSN, we just understand what phazon codes are and how they're created, and we understand the first principles, but we haven't gotten around to doing that. But the phazon code should be describable, I think, by Fibonacci anyons. Marcelo suspects that as well.